here is the first example from Stokes theorem. Now we are given a surface S, which is the portion of the plane x plus y plus c equals to 1 in the first octant, and C is the boundary of S, traversed counterclockwise as viewed from above. Okay, let's draw this surface first. This is our famous surface x plus y plus c equals to 1. That's a plane. Okay, so we have this plane. If you and if you view from the above, the path of this boundary traversed counterclockwise direction, which is this. Okay, and this will give you a positively oriented curve, therefore outward pointing normal vector, something like this. So this is your n, which is what we want. Okay, this is your curve C, and we have a vector field F. Oh, I forgot to give you the vector field. Use Stokes theorem to calculate f dot ds. Let's complete that, where your vector field F equals to negative 3/2 y squared minus 2xy comma yc. Okay, good. Now on this surface we have a vector field F. Now we want to use Stokes theorem to calculate this line integral f dot ds over the curve C. Okay. Now Stokes theorem. Okay, so this is a closed curve. So we usually denote a closed curve using that symbol. Line integral over a closed curve using this symbol. Sorry. So now Stokes theorem says line integral over the closed curve C of f dot ds, this equals to a flux integral over the surface S. Now what is your S? Your S is this part. That's your surface S. The integrand should be curl of f dot nds. So we need two things. Actually, we need to calculate the curl of f first, and then we want to simplify this n dot ds term. Okay. The equation of the surface is, so this surface is x plus y plus z equals to 1. So let's express the z coordinate in terms of x and y, and this is your little f of x comma y. That's the surface. Now we know that this flux integral can be converted to an area integral over a domain D. Dot here you should get minus f sub x minus f sub y and 1 dA over the domain D. Okay. Let's calculate the curl of f. Let's calculate the curl of f. So let's calculate curl of f, which is gradient cross f. This equals to ijk And in the second row we should have the components of the gradient operator, and then the components of the vector field, minus 3 of y squared, negative 2xy, and yc. So let's calculate this cross product. So curl of f equals to, okay, so I times partial over partial y of yc minus partial over partial c of negative 2xy. That's the first component. And then we have minus j times partial over partial x of yc minus partial over partial c of negative 3 over 2 y squared. Finally, the last component equals to partial over partial x of negative 2xy minus partial over partial y of minus 3 half y squared. Okay. Okay, now let's take this partial derivative with respect to the y. So then you should get c minus 0. Derivative of negative 2xy with respect to the c variable should be 0. And if you think about these two partial derivatives, you should get 0 as well. We can treat the product yc as a constant with respect to the x variable. We do the same thing for this one. So then the second component is 0. So that's the second component, 0. And the third component becomes, so you will get, let's use a different color, minus 2y plus negative times this negative becomes positive. So we have plus 3 half times 2y. If you simplify this, you should get c comma 0 comma y. That's the value of the curl of f. Okay, next we need, so at this point we have curl of f in hand. So let's calculate these two partial derivatives, and my f is 1 minus x minus y. So now f sub x should be negative 1, f sub y should be negative 1 as well. Now we are ready to evaluate this flux integral. Okay, and now we have to evaluate this curl of f on the surface. On the surface, c coordinate is given by 1 minus x minus y. Okay, this should be negative of negative 1, which is positive 1. This should be positive 1. This is positive 1 dA. Now, as I mentioned earlier, this c value is 1 minus x minus y. Because we are evaluating this surface integral on this surface S. So on the surface S, c coordinate is given by this function 1 minus x minus y. So now, okay, so this is over the domain D. This becomes, okay, so we have 1 minus x minus y plus 0 plus y, the domain D. We can eliminate y. So basically we left with 1 minus x dA. Now let's look at what our domain D is. So domain D is on the xy plane. The domain D should be, this is a different color. Domain D should be this part, this right triangle. That's your domain D. And so basically you will see something like this. So this is the x-axis, that's the y-axis. Then equation of this line should be 0 equals to 1 minus x minus y. In other words, y equals to 1 minus x. So this is your domain D. Let's consider an area element dA. Now this double integral of 1 minus x dA over the domain D equals to 1 minus x times dy dx or dx dy. Usually I choose dy dx. Y goes from 0 to 1 minus x. X goes from 0 to 1. This is 1. Okay. So let's evaluate this. You should get 1 minus x times y. Lower limit is 0, upper limit is x. Apply the upper limit minus the lower limit. You will get 1 minus x minus 0. So basically you will get, your new integrand becomes 1 minus x quantity squared dx. And if you evaluate this integral, you should get 1/3. So try to FOIL this. You will get 1 minus 2x plus x squared, which is this part. Now if you integrate this, you should get 1/3. Now this is the way we use Stokes theorem to evaluate a line integral over a closed curve of a surface S.